Hi, AP Chemistry students. I'm going to show you another equilibrium type problem that you might see on AP exam or on your test at the end of the week. It says, answer the following questions about the solubility of silver chloride. The value of the KSP of silver chloride is 1.8 times 10 to the negative 10th. And that, of course, means that silver chloride is very insoluble, dissolves just a very small amount, but we want to find out what that solubility is. So we're going to start with A on this page here, and A just says to calculate the value of the concentration of the silver in a saturated solution of silver chloride in distilled water. So the first thing I would do for A would be I would write out the dissociation. And then I would do a short rice table. So there's the reaction, ICE. This is a constant, so we really don't care about it. We also know that however much this dissolves, its solubility is going to be the amount that you get of the ion. So we start out with 0 of each of these, and the change is going to be S and S plus S. So the equilibrium concentration in distilled water is just going to be S and S. All right, now if we have KSP, the KSP expression, which is going to be just the silver ion concentration, the chloride ion concentration. And if each one of these is S, then the KSP is just going to equal S squared. And so since the KSP, as we see up here, is 1.8 times 10 to the negative 10th, then we're just going to need to take the square root of both sides. And the square root of both sides is the solubility, or also the concentration of the Ag+. And so that's going to be 1.3 times 10 to the negative 5th molar. So that's A. Okay, now let's look at B. This is where we use a common ion effect. So remember, we just calculated the value of the silver in distilled water, and that was 1.3 times 10 to the negative 5th molar. Now they want us to calculate the concentration of chloride in seawater. They want to calculate the molar solubility of silver chloride in seawater, knowing that the concentration of the chloride ion, which is a common ion with silver chloride, is 0.54. Okay, so what we're going to do is we're going to make another rice table, because I like rice tables. So again, the idea here is that this is the dissolution. Again, this doesn't matter because it's a constant. In this case, the silver is starting at 0, but the chlorine, since you're in seawater, is starting out at 0.54. Solubility is still going to change in the same way. The change is going to be S and S, but therefore the equilibrium concentrations are going to be S here, but 0.54 plus S here. Now, we're going to use the small number approximation. Since we know that the solubility is very, very small, we are going to just sort of negate this portion. And we're going to just assume that the chloride concentration is very, very close to 0.54. So then when we write the KSP, which is equal to 1.8 times 10 to the negative 10th, and it's going to equal the silver times the chlorine. And in this case, it's going to be S and 0.54. And so then when you solve for S, it's going to be, S is going to equal to 1.8 times 10 to the negative 10th divided by 0.54. And I'm going to put that in my calculator. And I'm going to put it in my calculator. So it's going to be 1.8 So it is going to be 3.3 times 10 to the negative 10th molar. And you can see that it is much less soluble. If that's the solubility as well and the concentration of the silver ion, you have much less than when you had in regular distilled water, and that's because of the common ion effect, essentially driving the equilibrium in the direction of the solid, and so making this less soluble. And that would be the answer to this last question. Explain why AgCl is less soluble in seawater than in distilled water. You want to reference the common ion effect, that by adding this ion to the equilibrium, you drive the equilibrium back towards the reactants, and therefore decrease the amount of silver ion that can dissolve in the solution. And that's the answer.